Let's see if the fire alarm goes off again during the talk. Thank you very much. So yeah, I work for Google. I left Lattice gate theory, I think, in 2003 or 2002. So that's a long time. It's sort of amazing to see that things that we discussed, or I remember being discussed in the late 1990s. Remember multigrid algorithms and speeding up the inversion of the fermion operator by preconditioning. There's still reverberations of that. I saw a few names in the citations that I remembered from long ago. But then I left Lattice gate theory. I had a longer time in structural bioinformatics. And then I joined Google, and I'm in a team that actually once was called QM, Quantitative Marketing. So we were actually part of the marketing organization. And I still work on topics on that. And I thought I would bring, that's actually a presentation I gave last year here at a completely different conference, Predictive Analytics World in Berlin. It's there every year, where data scientists come together that often work in areas of like online marketing, online advertising. And I brought this presentation because I think if you look at what we're doing, there's some reverberations of physics and even lattice theories in there and how we do things. So what we are interested in if advertising works. We are mostly interested in that because our clients pay us for the advertising. So it's generally quite important to sort of demonstrate, at least in some way, that it works. That's the argument that it obviously works, because otherwise they wouldn't be paying us for that, but that's not something good to tell the clients. So what we are interested in finding out whether advertising works at all, or if you can actually measure how well advertising works. It's actually a very hard question. It's traditionally a very hard question, especially for offline advertising, like the classical TV advertising, billboard advertising, because it's very difficult to measure if there's any correlation between your advertising spend and your sales. Generally, your sales are relatively stable, especially if you like people who spend a lot of money on advertising. These are what you call CPG, consumer packaged goods. That's what you buy in a supermarket. That's a huge amount of money flowing out from companies like Procter & Gamble, PepsiCo, a few others. But they basically have no direct way of checking whether the advertising actually works. And understanding online advertising, it was much easier at some point, because the first online advertising, that's the advertising you know from Google search, from banner ads. Yeah, basically, you just need to track whether people click on that and buy something afterwards. And then it was suddenly much easier to sort of give people an indication whether the ads worked or not, because we could tell them, yeah, somebody clicked on that ad and bought something in the end. Do you see? The central question, that's something that's very interesting for statisticians today, is the question of the causality of this correlation. So does it really mean that if somebody bought something because they saw an ad? Or is it just that we showed the ad to somebody who was likely to buy the product anyway? That's actually one of the central problems in online advertising, because we have very intelligent computers. These computers are tasked with optimizing our revenue. Basically, we're getting paid if somebody buys something. So the computer is supposed to show the ads to people who are susceptible to the advertising, like they can be made to buy the product. It might also just choose to show the ad to people who anyway buy the product. And to differentiate that, we actually have to look at experiments. So this is something that economists are really interested in the last 10 or 20 years, how you can actually measure economic things by means of experiments instead of just observing. So the classical way of figuring out whether an ad works was basically just to split your population into two groups, an exposed group and an unexposed group. The exposed group sees the ad, the unexposed group doesn't see the ad. It might see another ad, it might see a public service ad, basically something that is not expected to make a change in their behavior, while the exposed group should change their behavior. And then we simply count how many people take an action, for example, buy the product. So we hope that, of course, in the exposed group, there are then more people buying the product than the unexposed group. The problem is, of course, there might be some people in the population that anyway will buy the product, whether they see the ad or not. And then the problem is basically if our ad server figures out who these people are, because they're in the right demographic group, for example, it will put them into exposed group, because it selects them as the group who sees the image. If it's just observational. At this point, we allow the computer to choose who to show the ad to or not. And then we will overestimate the efficacy of our ads because these people will end up in the exposed group and it will look like we made them change their mind, whereas in reality they didn't change their mind. So the important thing at this point is that we need to randomize when we split in the exposed or the unexposed group. At that point, they become a treatment and control group. So now, even if there are people in the population who buy the product anyway, some of them end up in a control group, some of them end up in the treatment group. And that makes sure that we actually get a realistic estimate of the efficacy of our intervention. And this works the same whether you do it in assessing the efficacy of a medicine or in the efficacy of online advertising. But how can we do that? The central problem is that to do that, we need to split the population into a treatment and a control group. For a long time, that was relatively easy to be done by using cookies. The famous cookies that are on your browser, and we get a lot of questions about. Because the cookie would stay on your browser in a relatively long time. So what we do is we would choose certain cookies who would form the control group. And these people that have these cookies would never see the ad. And the other cookies would be exposed to the ad. So we will get no control group. But that's something we don't really want to do because it involves that thing that you need to sort of track people. I'm carefully to use that word, but yeah, in some sense, if you want to do an experiment like that, you have to be able to identify people in the control group over a longer period. It also has the disadvantage that it does not account for all the other advertising you might be seeing. So that was the idea, and that's at the same time scales as we're talking here in Lattice. So it started in our team in 2011. That's actually paper links here, so this is published. The idea of doing a geo-experiment. The idea is we choose different regions in a country. And in some of these regions, we actually run the ads. And in some of the other regions, we don't run the ads. So we split the country in different regions. We sort of randomize over that. Instead of having to track people, we just rely on, and this is what most of this talk will be about, rely on that people don't move around very much, at least not over distances of a countrywide. And we have the advantage that in online advertising, we can often sort of figure out which city at least people are in from their IP address and other signals. And we can even combine it with offline advertising, offline revenue. Because in theory, but though actually I don't think that's ever been done, our clients might choose to say, okay, we have chosen these cities as part of a control group. We also don't run offline advertising like billboards or TV there. And they can actually look at revenue at stores instead of just online revenue, but just looking at the stores in the different regions. So we compare the revenue in the regions where we don't show the ads to the revenue in the regions where we show the ads. Then the interesting problem is now, how do we choose these regions? And I was mentioning that it relies on people not moving around very much. And for example, in the US and in Germany, you can use the states or the Länder. But it turns out these are very different structure. Like Hamburg is a state of its own, and so is Niedersachsen around it. These are completely different sizes of places. What we found is that somehow we need a computer algorithm that gives us the optimal decomposition of a country to minimize the moving around of people. And it turned out that it's an interesting problem. It's maybe not probably a machine learning problem, but it was a very interesting physically inspired problem. So our goal is now, how do we decompose a country into regions so that people stay most of the time inside the region? And obviously, we want to have a covering of the country in the end. Every place in the country needs to be assigned somewhere. And also, we want to be able to randomize. So we need a certain amount of different cities. So we don't want to just a country split in two. We want to have like 20 or 30 regions. So how do you do that? And how do you do that from a first principles approach? So I'm going to talk about two things that sort of reflect the physical approach to that. The first question, what is a good geography? So what would be our measure, our Lagrangian or Hamiltonian in the end? The second is, how do we solve that? How do we find then the best geography? So we call this actually contamination. Contamination is this effect that contamination is a term coming from medical experiments. It means that if your control or experiment group does the other thing round, so the people in the control group actually do take a medication, and especially the people in the treatment group don't take the medication. Contamination means that these groups are not pure anymore, but they are contaminated with people that would have belonged in the other group. And if you have contamination, your group sort of dilute and your signal goes down. That's what you want to avoid. For us, contamination means the possibility that, for example, somebody stays in one region for some time, they see an ad, but then they actually spend some time in another region where we don't show the ads, but they still buy the product. So then it looks like that in this untreated region, there's a higher revenue than would have been without the advertising. We want to minimize that. We want to minimize that in a systematic way. So how do we estimate contamination? So when I started the project, the computer scientists had simply set up a completely ad hoc model. They were simply, I think, like counting how often people move from one place to another. But I thought of it, when you think about it as a physical problem, you can actually think about, can we sort of observe how people move around in the country, and what can be inferred from that? The first idea was that somehow on a macroscopic level, you spend money in some regions, and this has then an effect in revenue, both in the region where you spend the money and other regions. So yeah, let's put a matrix in the middle. So somehow, instead of normally, this matrix should be diagonal. So you spend money in a region, and the revenue from this spend, from the advertising in that region, ends up in the stores or in the people in this region. What now happens is, if people move around, I expect that there's some sort of distribution matrix, that if I spend money in one region, there might be an effect on a neighboring region. How can we estimate that? So this is actually original slides. I didn't change these slides for this talk, but you see the word two-point process in there. So I was about to write two-point function, but people wouldn't understand that at all. But yeah, what in the end happens is we are interested in spatial processes. So people get exposed to an ad in one region, and then they move to a different region. The idea is now we can actually then look at people's motion over the country over time, and we have this data from different sources, especially just from advertising sources, and we get like a joint probability distribution that a person is at one time in space at one point, and then another time at another point. And then you see sort of the connection to field theory. That's, it's sort of inspired from that. And for the statisticians, then you sort of marginalize, so you get a dependent or a probability distribution where people end up if we see them at a certain point. Here's an example. So I have them just, so there are 3 users, and they have ad exposures now in different states of Germany. And in the end, you can turn that into a mixture model where you basically just count for each of them what is the distribution of the expected presence in the different countries and the different parts of the country. So I know that, for example, this first user was 4 times in Bavaria, 2 times in Baden-Württemberg, and so on. And this gives us, in the end, the matrix that just specifies to me for each user how often they ended up in each place of the country. In statistics, that's called a mixture model, because basically you have these different users, and each of the users will have a different profile, how they travel around the country. There's actually a problem with a colleague who came from physics, who said, oh, that looks like a random walk. No, but it isn't a random walk, because this distribution is not a random walk in a sense. So every morning I bike 6 kilometers to work to the west. But then in the evening, I don't randomly decide to bike another 6 kilometers to the other half of Hamburg, but I bike back to home. So the distribution of where I am is basically not dependent on where I am before, but it's dependent on the time. So in the morning, I go to work, in the afternoon, I'll go back, but the distribution is just centered around these 2 peaks, and that's what this would show. And what you can then do is, you can combine all of these distributions in a joint distribution. This is a matrix now. We're summing over all the different people. I'm basically summing how often people appear in one region and then in another region. And it's not even time dependent, because I took out this degree of freedom. In theory, the people have always asked me, shouldn't that be time dependent? So should that be that you have to be in region J before in region I? But no, that's just a complication. It's an abstraction process. And in principle, what I just get is a correlation matrix, like a 2-point function that tells me the probability that a person in some time is at place I and at place J in a certain time segment that we are interested in. And we normalize that. Yeah. And this then turns into what we call a co-visits matrix that sort of gives you the probability that somebody visits 2 different regions. The interesting thing is then, once you have a matrix like that, you can then actually use that to quantitatively estimate the probability that somebody who is exposed to an ad in one city, then later on travels to another city and maybe buys something there. Sort of going a little bit gloss over that because that's not the main part. And you, in the end, get the flow matrix that basically just describes you spend advertising money in one region, and some of this money then flows to another region. So here's a nice example. So that's what that's what the matrix looks like. So the right is the normalized form, the left is an unnormalized form. So this is, of course, it's a matrix in space. So it's a four-dimensional matrix in some sense. And I fixed for 2 dimensions on the location of my house in Hamburg. And the diagram shows you, especially the diagram on the right, which is improperly normalized, it shows you the probability that somebody who would be in Hamburg in the same time period would be in other places in Germany. And you can see, for example, the outlet, so on the top, the metropolitan region of Hamburg. These are people traveling for work. You can also see, like, even Sylt shows up there as a dark blue dot on the top left. These are people going for weekends or for the holidays. And the tentacles that go to the west and the south, these are the motorways. Because there's a relatively high likelihood that if people travel on motorways, they sort of turn up in the same day in all of these locations. You can sort of follow the main motorway down to the Frankfurt region. It's also interesting that was work we did in 2020. This plot when you do it on a weekly basis starting in March 2020. So these are real data. What you see is that due to the lockdown in 2020, there's a complete breakdown that we saw of traveling in Germany. Basically, within a very few weeks, all of this correlation went down just to what here remains is basically the metropolitan region where people travel to work. So it was quite impressive that we saw that. Now we have this matrix. This matrix now describes how likely it is that money you spend in one region moves to the other region. We want to build these nice regions where people don't leave the regions likely. How can we describe that? So as I said, this matrix is a flow matrix. It basically describes if you spend some money in one place, you spend some other. What we can do is we can rearrange now the matrix to sort of concentrate the large matrix elements as close to the diagonal as possible. So that's not an unusual transformation for a physicist. Okay, we actually use that in bioinformatics too a lot. So basically, we're trying to block this matrix. We're trying to rearrange that matrix so that the large elements are close to the diagonal and the small elements are off the diagonal. And then what we then would do is we would say that all these blocks form a region. So the first 3 entries here would form one region. The next 7 entries would form the other region. The last 2 entries would form the third regions. And the idea, we can actually show that there is a blocking. We can, this big advantage of how we defined this flow matrix was that if you do blocking, it has a recursion relation. So the effective flow of the advertising dollars between the different regions after you do blocking is, of course, just if you sum up the different matrix elements in each block, and you get an effective matrix. What we get from this is a measure of contamination for any sort of partition of our data sets. It's the off-diagonal elements. So the challenge of the algorithmic challenge is basically rearranging your matrix in this form that the off-diagonal elements are smaller than the diagonal elements. It's actually quite a physical realization of the problem. So how do we solve that? So indeed, there was an original method that we used. Does that work? Yeah. That was simply an ad hoc method where you joined, like, you looked at this matrix and then you put like the 2 rows next together that are most similar, and then you did this again and again. And what happened is that worked for some countries, but other countries, like this is the Netherlands where we did this data, they developed something we called the blob, which was the problem that one cluster grew and took over everything else. So we were actually then looking for an alternative approach that was able to split the matrix from the top instead of doing this bottom-up approach, because we felt from an intuition that in a very densely populated country where many places are very close together, you have to do a top-down approach. So the method we in the end ended up was you use spectral clustering, which is actually, and you see here diagrams that start looking like lattice diagrams. They're not lattice diagrams, but there are relationships there. So we can also reformulate that problem of finding the optimal clusters for the geographical entities as a graph cut problem. And of course, every matrix can be represented as a graph. It's useful if many of these entries are small or close to 0, because then it actually looks like a graph, simply by sort of taking the elements of the matrix as the edge weights. And then just, for example, put a very simple graph here that has sort of a reduced matrix. And as I said, what we want to do is we want to sort of cut this matrix somehow, or partition this matrix into 2 sub-matrices so that the off-diagonal elements are as small as possible. You can reformulate that in a graph that's simply a cut of the graph. So you want to sort of take your graph and you cut it in the middle. Half of the nodes or some of the nodes end up on one side, the other nodes end up the other sides. And then if you think about it, the nodes, the vertices that you cut are the off-diagonal elements because they're, one of their indices is in the one data set and the other is in the other data set. So they can actually be revisited as a graph cut problem. So graph cut problems are a big thing for computer scientists, and it's also sort of interesting to see that all the solutions that the computer scientists found are generally correct. They have an estimate of how quickly they converge in ON notation, and they're generally useless. Because it's not only that they converge very, very slowly, it's often out there sort of they generally converge to solutions that are not always very good. Whereas, on the other hand, if you come from a physics background, you're thinking, okay, do we have any sort of approximate or random or randomized algorithms? And there's actually one famous algorithm for splitting a graph, which is based on the eigenanalysis of the graph Laplacian. I'm trying to sort of explain that a little bit. This talk is not meant for physicists originally. Let me put in a digression why that has something to do with machine learning. Our problem, as I formulated it, is to sort of minimize the distances of objects, maximize the similarity of objects in one group, and maximize the dissimilarity between the groups. This is a problem in machine learning for unsupervised machine learning that has been around for a long time. One example was 20 years ago, people were looking at gene expression profiles and trying to figure out, gene expression profile means that you have the level of expression for a large amount of genes in a cell, for example, in a yeast cell, and you measure that under many different conditions. Then you get these diagrams on the x-axis, the horizontal axis. You see the expression levels of different genes. So a gene is shown as green if it's up-regulated, and is red if it's down-regulated. And on the y-axis, you just do all sorts of different conditions, like you heat up the yeast, you put acid on it, and you just collect this data. And what they were interested in that time was sort of also similar to us. They were trying to figure out a network from these genes. So you have these patterns, and where are the similarities in the pattern, where are the dissimilarities? A typical machine learning problem. And if you look at the history of machine learning, you can even go back longer. So this is a paper from 1932 about the quantitative expression of cultural relationships by A.L. Grover. He was, I think, the first anthropology professor in Berkeley in 1932. And what they did, they actually created a matrix that's quite different to the feature matrices that we use in machine learning. So these are the tribes of northeastern Peru. I think there's something like 40 of that. Like each row is one tribe. And then on the y-axis, in the columns, are the features, the properties of these tribes. So this is actually the other way around. Normally we would show that the other way around, but on the rows are the features. So there's always a feature description of different, like how they marry, who is allowed to marry whom. And so it's actually quite interesting. And on the y-axis, the axis, these are all the different tribes. And whenever a tribe had a certain feature, they would put an X in there. And if it didn't have the feature, they would put a minus in there. They also demonstrated one important thing in data science. Never collect your own data. So if you notice, this is an English language paper, but this is in German, because they simply took a previous paper that collected all this data and just put it in there. I mean, sort of cited that, but they realized that this data is already out there. And the idea now was, can we, by looking at this matrix in a very similar way, we would also do that for gene expression 50 years later, can we somehow figure out how these tribes belong together, which were similar and which are dissimilar, which came from one another and which didn't. And so what they did do, they basically looked at all the pairs of the tribes and counted the commonalities. So then they had the correlation matrix that has like n times n, so you have n tribes, so you have n squared elements, so n times n minus 1/2 different elements. And they would simply rearrange the matrix in the way that the rows that were most similar were next together. So very similar to the problem I had before with rearranging our matrix so the high correlation coefficients were close to the matrix, close to the diagonal. And it actually worked in the end. They could show that by the clusters they found in that way correlated to the geographic location of the tribes. So the tribes that they identified in that way to belong to the same cluster because they had high overlap in the commonalities turned out to be also close together. And that was sort of great because they could prove that they wrote that down at the end of the paper. They had a simple statistical treatment that will allow others to reach objectively founded general interpretations. So this is basically machine learning or to some extent statistics. Yeah. So that's what you just explained. So they go from the features to a similarity matrix that then you can interpret that as a graph. And then they do the grouping based on the similarities. So you want to have the high similarities close to the diagonal, low similarities off the diagonal. So, and how do you solve that now? In the interest of time and the fact that you're all physicists, I don't know if you have sort of heard about random walks about graphs, on graphs. So you can imagine what happens if I have a graph like that. So that's an example. And of course, in the end, we know that we want to cut in the middle. But the middle is a strong link, actually. So it's one of the strongest links in here. But it's quite obvious that the two groups you should have are the left and the right. So if you imagine now, and that if you put a random walker on this, that sort of starts at a node and then transitions to another node based on the strength of the link, what happens is that a random walker will spend quite some time on the left, and then at some point it will go to like the middle, and then it will jump to the right, will spend some time to the right. I think we saw several times today like these plots where you have the topological charge and the transitions. And of course, if you want to solve that, in case here everything is nicely linear, you can just look at the spectral decomposition of the transition matrix. And well, what happens is, you look at the eigenvalues, you turn it into a stochastic matrix for this little random walker, you look at the eigenvalues, and it turns out that only the lambda equals 1 eigenvalue survives in the long term, which gives you a trivial eigenvector, but then you could look at the next lower eigenvalue, and this then sort of gives you like the slowest decaying mode over this graph. And if you look at the graph, you would expect like the slowest decaying probability distribution is like where you have the walker either on the left or on the right. Yeah. So this is that's like the lowest node. And the trick is how you do graph decomposition with that is that you basically look now at the stochastic matrix that defines our graph. It's like with the proper normalization, everything. Then you look at the eigenvectors. The second eigenvector gives you this sort of Fiedler vector that, and I showed it here in the graph, this vector indeed sort of separates the graph from the top out. So it can actually feel from the top which of the graph is connected more, or which parts of the graph are connected more. And you can then apply that in different ways. So you can use more eigenvectors and then find more components of the graph, or you can just do it iteratively, so that you look for the best cut of the group from the top, and then you do that again for the groups and split them, which we did here. And so this is actually real data. This is actually the Midwest region of the US, and it's the chain stores of a large American store. And what we were looking at is this probability that people move around from one, so to say, close to one store, and then sometimes they're closer to the other store, and so on. And it works. So we calculate our correlation matrix and so on. We calculate the Fiedler vector, which is the picture on the middle. You see this gives you already, it's basically heuristic. So it's a slowly moving number assigned to each node, so that if you would go from the bluest to the reddest, you would smoothly move to the region, which is sort of a nice spatial interpretation of a matrix. It's the lowest mode of a resonance in there. And then you just threshold at a point of your choosing, and then you can actually split the region. And you see in this case, it would split off, actually I forgot, Urbana-Champaign is something there. The big thing in the middle is Chicago. And you split them off. And that then works. And this, for example, here is, this is by hand. So this is that's not a movie, I can do that by hand. This is an example how the US gets split using this algorithm. So it starts out by removing the islands. So this is Hawaii. This, I think, is part of Alaska. And then the first actually major split, and that was a nice success, it really nicely split the US down in the middle. So this is only coming from the correlation data we initially sort of calculated between the different locations. How likely is that people are close to one location and to another location? So basically it's distance. And the algorithm was still sort of able to immediately from the top, by looking at this data, split the country in the middle. And then, is that a movie? No. And then we sort of repeat that, and we see that over time, like the different major regions are being split. And it sort of respects population density. So you see sort of the northeastern seaboard is really hard to split. So here California splits into two between these two, the Midwest splits. And then we go on until we sort of have regions that are small enough to serve as our experimental units, if you remember, like the beginning of my talk. And I have this as a movie, so I like this. It's sort of hypnotizing. And so the interesting thing is there's a sort of a long way. I started out with ad experiments, and then we had to think about how to, the problem is actually to finding these regions, and then we need to define a useful measure of how good a split is, not just based on distance, but actually being on measurable data. Then we turned it into basically a physics problem or math problem from your perspective. And at the same time, it has a relationship to machine learning, not the neural network learning that we normally hear about it, but it's just one of the central problems we have in an unsupervised learning, that we want to create, just look at data and figure out which data belong together and which are different, where there are signals. Yeah. Okay, this is not so explained. This is Germany. One of the interesting things from a physicist's perspective was there's a measure of the effective, it's not 10 minutes. So I'm actually nearly to the end. One of the interesting things I found as a physicist was that, so if you measure the contamination is the measure of how bad your clustering is. And obviously what happens, the contamination increases with the number of your clusters, because your off-diagonal elements increase. So what we normally see, if I look at the number of clusters, the more clusters I have, the more, like different regions, the more, of course, contamination is, the more likely is it that a person travels across a cluster border. And of course, we want to find a balance. For our algorithms, this is completely another thing, like 100 clusters would be good because we randomize. So we want to actually sample from this distribution to ensure that we don't have artifacts in the data, confounders, statisticians call them. So we find this plot, and it's a typical Monte Carlo plot. You see these things like jumping up sometimes when there are things plot. But of course, what often happens is that these splits are uneven. So we might split a large data set, and we split off, like you saw in the beginning, we split off Hawaii. So that's a very small split. It actually doesn't change the effective number of clusters very much. And there's actually a definition of the number of clusters, an effective number, based on entropy. So we basically measure the information entropy in your distribution based on the number of population in each step. Again, the same thing as entropy in physics. Basically, if you have only one cluster, you have zero entropy, and then optimally you split that cluster into two, so your entropy goes up. But if you split that cluster into a 90% and a 10% cluster, your entropy doesn't go up that much. And you can actually turn that into effective number of cluster. So if you do a perfect split, you go from 1 to 2, or from 2 to 4. If you don't do a perfect split, you go from 1 to 1.1, 1.2, and so on. And then suddenly, the curve becomes smooth. So I found that quite interesting. I don't really have time to do like the physics behind that, but somehow this effective number of cluster basically turns the contamination, the sum of the off-diagonal elements, into a relatively smooth curve that's basically just linear where you can measure the coefficient. And so that was, from a physicist perspective, quite interesting. Yeah. So what I wanted to show here was that physics intuition is actually useful in a quite surprising number of fields, I found. So the people that I work with are a mixture of statisticians, computer scientists, and physicists. The statisticians often have very strong ideas and a very strong background in a lot of figuring out what's correct. So they're very, very about whether you have confounders in there and if your statistical conclusions work. Computer scientists are very good about speeding up algorithms, but they have usually a big problem with data, because from their lectures about databases, you're used to looking at data as something that's always perfect. You put the data in the database, and they're there, and then you search for them, and the algorithms are about correctness, not about speed. And they really have trouble dealing with anything that's probabilistic. So physics is sort of a sweet spot in between. We understand probabilistics, but you also have sort of know that we need sort of a physical intuition about what we want to have in the end. And this algorithm was an example of that. And I found it just interesting that it is a classical machine learning algorithm, spectral clustering. It allows us to look at data and understand data. It's interesting to think, and I'm thinking of that at the moment, instead of doing the classical way with the spectral decomposition, could you, in the same way as we heard in the previous talks, could you use machine learning to actually learn this way of splitting the matrix? But this is something that you need time for. And I found an important thing was to understand the problem from a physical point of view. So especially in the beginning, when I talked a little bit about how we derive this matrix, that was sort of informed by how physics works underneath, how things move forward. Basically, it's a transport process, because people are moving around in a certain pattern. They pick up like an at exposure at one place, and then they drop it off as a conversion, as we call this, or the event exit of buying something at some other place. So I hope I could give a little bit of insight how we use physics in marketing in this case. And I think we can go to the questions.
Okay. Thanks very much.